to some extent of complexity, we can test that using FPGA. That means prototyping sort of thing we want to do. Before that, the functionality test you can do using FPGA. So now this PLDs, we have something like a two-layered element where we are having, sorry, this AND or logic, that means your SOP format or POS format, if you are implementing AND or logic, you are having a partial programmability. Something like AND gate is fixed and your OR gate you are trying to program according to your Boolean equation. That is for your PLD. Now, this is something like to the extent of what you can say a lower level of complexity. But this FPGAs, it will be used for a multi-level logic, like more complex compared to your PLDs. So what we need, or what exactly FPGA needs, is a segment which is programmable, and the segments interconnectivity. That means programmable segments has to be there. That means logic blocks has to be available, and the interlinking of the blocks. Okay, what are these logic blocks is like the complete system when you're taking that into some basic building block sort of thing. And these blocks, if I take we can call them as logic blocks. And these logic blocks are to be in a position to be programmable. That means you have to define your own logic according to your design. And what is the connectivity between each block has to be available. And if that sort of thing like is available for us, now we can implement this to any level of complexity. So this PLD is for fixed, we are saying. That means you have something like the interconnects are already defined in terms of AND or logics, and you will be trying to blow the fuses or put the fuses intact according to the logics. So on the whites, you will be programming them according to your Boolean equation. So this comparison of FPGA with your a basic microprocessor, if you can take, the instructions are stored in the memory, and through the CPU, the instructions will be processed. Whereas for your FPGA, that like if I take this as comparison between a microprocessor and FPGA, this is something like program-based iteration we are doing, but here we are doing logic-based iteration. So there should be a combinational logic segment, like when we are designing the circuit, we try to put that into the logical blocks, a combinational logic element, and there should be a segment available on that logic to program that combinational segment. So when we are dividing that like complex to design into a smaller segments which we are able to manage, each segment becomes a logic element, we can say. This is a combinational logic or combinational logic element or combinational logic blocks, many synonymical names we have. So these blocks, when we are defining, should be in a position to be connected properly in order to make a top level design. That is the meaning of our testing. Now these becomes like there should be an interconnectivity between each logic block, so that there can be like what you say, a properly linked signals that are mutually dependent upon the iterative values, what is being the outcome of one iteration sort of thing, or multiple iterations if you can specify. So for testing, we need all the iterations to be evaluated. So that means that we need a programmable logic block, and these are programmable logic blocks, if you say the logic elements. These are the programmable bits, or what you can say the interconnects which are connecting these combinational blocks. Okay, now when this logic plus interconnect completely put together, we are saying that it is a FPGA block or FPGA segment, which we name it as fabric. fabric is nothing but the logic and the interconnect. That means the logic element and the interconnect put together is called as a fabric. That is the technical term we give for the complete design, or what you say, the combination of logic and interconnect put together. And now see here, this if you take the CPU and the microprocessor, in combination of that is used to store the instructions, okay, to perform your logical segment. Whereas here they will be taking the logical element, as I said earlier now. So there won't be any type of fetching of instruction as the microprocessor does. Normal, I think in previous classes I said that there should be an opcode coming in, and that opcode will be specifying what is the instruction that has to be performed. All those stuff is there. No? That sort of fetching instruction is not needed on when an FPGA testing is done, okay, because the structure itself will be storing what is the type of logic we are implementing. That means the connectivities between the logic blocks itself defines what is the design. So it will be something like an interwoven element of the logics, and say that structure we name it technically as the personality. Okay, the element of the, what you say, complete design, we call it as personality. So what is the logic you are performing will be completely or directly stored in that what you say, the function and the connection what you are mentioning. That means is this segment you are designing, or the FPGA itself is inbuilt. Some standard blocks will be there. You connect them together to derive your logic. That is the way we are performing the testing. So these FPGAs are programmable, we say. Why? Because the structures are standard, parts are there. We try to program according to our need or our logic by properly interconnecting those standard elements or standard parts. Okay, what can be the standard elements? The logic gates, the operators, what you are performing, ALU operations, all those will be incorporated in your segment of the standard parts. Okay, now when I want to perform or do multiple logics implemented, I can reprogram this as many times as possible. So what we can say is something like it is configurable, we can say. Programming means configuration. We can reconfigure that for multiple number of times. So we have few different types of FPGAs in itself. Something like if it is permanently programmed for a specific function, few of the iterations where we need them to be unaltered in the design, say, then such type of logics a permanently, or what you say, a company programmed FPGAs are available where you cannot reconfigure them. So normally for testing we don't go for permanently programmed, whereas like if this permanently programmed is one part of your circuit, then you can use it, but you cannot refine or redefine the logic there. But reconfigurable sort of thing is that we can change, or we can redefine the combinations, or we can reconnect them according to the logic and all. Now, what is the flexibility in your FPGA is that when you are reconfiguring, there is no need for the complete logical elements or the FPGA to be removed from the circuit or from the complete database, or data in the sense like hardware setup. On the what you say, board itself, you can reconfigure it. That means it is you can call it as on-fly reprogramming sort of thing. There is no need for the FPGA to be removed from the circuit and program. You can program it while it is in use itself. Okay, so Here, something like if the logic that is implemented on that FPGA is of a simple or less complex logic, then we say that it is fine-grained logic. Fine-grained is a simple, less complex logic implemented. We say that it is fine-grained. If the circuit complexity is increasing, and if you want to use the complete chip area in a more efficient way, or a denser circuits has to be used, then coarse or coarse grained logic will be implemented. The type of FPGA is called as coarse grained. Okay, these are two types of what you say um, logic based or complexity based FPGA that are available. Okay, something like platform FPGAs are there where along with the fabric means what is that fabric? The logic plus the interconnect put together, we are naming it as fabric. Along with that fabric, if the CPU is incorporated, this CPU will be storing the uh, program or the software on which the this testing is done. Okay. Someone has unmuted their mic. Please mute it. Na? It's giving disturbance. Okay. A platform FPGA, it will be typically including a CPU, and some of the functions wherein it is run on the software, that program will be stored on the CPU. Okay, something like a specific control segment iterations have to be performed. That sort of programs that you can predefine or store that in CPU, and you can implement or dump it on your logic block and find the output. Those type of FPGAs, we call them as platform FPGAs. Okay, when we are speaking about these FPGAs, what are the, sorry, okay. Like something like when we are speaking like testing of the designs or developing a prototype sort of thing, what are the goals or what are the like complete set of elements that are needed for us is something like we need to get a performance sort of thing, the performance of the design we have to see. That means at what rate the iteration is performed, or like in several ways we can say that means speed, efficiency, or power consumption, or what you say space, or something like pins, wiring. All this comes into picture for the performance analysis. Okay, or something like clock rate, at what rate of the clock duration that design is performing. Is it slow or fast sort of thing? I think we said static designs we are supposed to design and all. That is like it is a measure. The performance measure has to be done. Okay, and what like power and energy sort of thing, if we are measuring, why we need this power consumption analysis, or the find how much of power it is consuming is, say if your design or if your complete circuit what you are designing is based on a DC supply, say like when you will be using batteries. So using a battery, how much of duration, or what is the battery life it will be giving if you are using that circuit, that sort of analysis you have to perform. So like few of the systems, even if it is not used, if it is not completely like used, partial use is there, or it is ideal condition also, some battery draining conditions also happens. That sort of analysis has to be performed. So power and energy consumption has to be analyzed, and design time we try to say is how much time these standard parts are needed to be produced into the market or released into the market, and how much time it takes the prototyping and all this will be tested on FPGA itself. Like the more the efficiency you get at the primary level of analysis, the faster the designs will be getting released into the market. That is the meaning. And the design cost also we have to see. Cost means how much of efficiency you are getting. Based on that, what is your space it is occupying and how many components you are having, all that decides what is the cost of your complete prototype or the complete design. And complete design cost and manufacturing cost are a little bit synonymical aspects, where when you are putting that into bulk, what is the manufacturing cost? Designing cost is testing come prototyping, it will be. And something like you have to test uh, how many levels of abstractions it will be able to, what is abstraction, multiple level of abstraction. Something like if you are specifying, say, from verbal statement, if you are taking how many iterations or how many logics it has to perform, or how many segments it will be there to completely implement that particular design from the specifications. That means the logic blocks are nothing but your abstractions. Okay. And something like how much duration you're trying to take decides also the cost also. Okay, so all these are the basic level of what you say design challenges or requirements what you have. Now, coming to your FPGA designs, here what we are supposed to see is something like when we are taking from the specifications is your verbal description. Now here this won't be giving any sort of what you say hardware sort of complete information. It will be specifying what should be the number of inputs outputs, as usual what we say. The specification will be indicating the input versus output sort of thing, and what is the logic it has to perform. And something like when you are performing like a system like development, if we are taking, we have some abstractions to be coming into picture, where we have to follow either any one style like modeling style sort of thing, and how exactly your system is behaving when you are defining that model. Okay, so it is something like the behavior of the complete, like the description what you are getting. Something like when a clock is given, what is the iteration it is performing, what is the output it is giving, that sort of all stories what we have seen so far, all that comes as the behavior block. Okay, then after this is the stage of simulation what we perform. We do a register to like a transfer of the function, wherein we are trying to fully specify the behavior of the design in terms of time. Okay, that means your sequential machines in terms of time you are performing, like how many number of gates are there, or is it within the clock durations we are able to perform the iterations. All this will be this register transfer logic. Okay, and this logic is when you are defining the blocks, when you are putting that into the gates, like how much amount of power is taken, what is the delay you are getting, power consumption, delay elements, or your cost, what is the space it is occupying, all this is analyzed at the logic block. Okay, and when it is satisfied with all the needed specification, then we try to take that into prototype, and we try to develop that into a circuit format using your CMOS technology, or what you say, the other technology, TTL logics, any logic sort of thing which is giving you a uh, high efficient design will be given out at this stage. Okay, so this will be taken for the prototyping and it will be tested, and after that a PCB layout is given that will be released into the market. So something like when you are able to condense the space or condense the complexity, minimization, you will be able to decrease the cost. That is the simple logic what we will be having. So this is the abstractions of the design, I can say. The design abstractions have these steps. From the specifications, find the behavior and do the register transfer, then go for logical gating sort of thing. Then you get the prototype, and after testing the prototype, go for the physical, what you say, design, complete design that will be released into the market. Now, this is what we are making it as something like a testing stage only. So, what are the methods what we will be following to achieve these things? Is, as usual, what we go for is either of go for a top-down approach or bottom-up approach. Okay, so or you can go for mixed style of approach also if you are not convenient with complete top-down or complete bottom-up. Okay, and when we are going for simulations, as usual, use your VHDL or Verilog programming for defining the what you say, the simulation and compilation and simulation segment without going for hardware. Physically, we will be doing the testing of the design. So while doing so, what are the goals? What we have to see is whether the design is functionally correct, and is it properly giving a time multiplexed sort of outputs, like for every instant, is it in a proper format, output generated or not will be tested. And not only that, doing so, what is the amount of heat that is getting generated, or is there any extra heat dissipation elements that you have to incorporate, also has to be analyzed. And doing all these iterations, is it picking some amount of noise or something like bugs, we can say? Is it able to perform without catching any bugs? Okay, and doing so, we will be doing some assumption sort of thing, or what you say, design considerations will be there. All these design considerations and assumptions, what you perform or what you assume in your designs, you have to do a documentation. This is again repeated elements what we are seeing in this segment also. These things what we have seen, these are all what we have earlier done in our combinational sequential designs or testing sort of thing. Now coming to our major segment of designs, that means something like a complete FPGA if I want to develop. What are the segments or what are the major elements that will be needed is a logic circuit, simple we say combinational logic block, and the connectivity or connections between them, and the externally used inputs and output terminals. Okay, these becomes the three major segments that are to be um, like incorporated when you are going for the FPGA designs. Now, these elements, these two, if you can take, we can implement using SRAM approach, or something like we can go for a switching mode sort of thing also. Okay. So SRAM approach, yesterday I have given the day before also. What is SRAM? What is the logic of SRAM? SRAM, don't remember. It is storing the data in terms of D flip-flop sort of thing. No? So that approach we can say, or an anti-fuse approach also we can for developing FPGA. Now, for both SRAM approach or anti-fuse approach, the input-output pins will be similar sort of thing. Okay, Normally this input output is how far this will be able to handle the input without loading itself, and how many segments it can connect without loading the FPGA. That is your IO pins that you have to look into. Now here, what is the segment, or what is the major um, element what we have to see is, when we are dividing the segments into the smaller manageable blocks. Okay, let it be any number of blocks you are taking in. These becomes the logic elements or the combinational logic blocks, and we try to use an interconnects which will be able to connect each and every block meaningfully. Okay, and each element should be having an input and output block. So I can say that this is IOB block, input output block we say. Okay, so this can be called as combinational logic block or logic element, and these are interconnects. This is as simple as that. Okay, now until this is okay, but coming to when we are interconnecting, what is the format that you have to follow if an block which is placed somewhere at the top left to be connected to the bottom right, say how many paths you have, and which one gives you a minimal path, which is minimal path means less delay. Okay, less delay and less wiring also we have to see. That has to be taken as your connectivity. So when you are taking this interconnects, it is not as simple as this what I have shown here. These blocks will be having in between the paths which are labeled or lined like this. Okay, this will be the interconnects wiring. So something like horizontal and vertical paths will be there. Now we have to define, like I want to connect this from this point to this point. So something like what a horizontal path, vertical path, horizontal path sort of thing. Like this becomes routing sort of thing. We call this as routing. This routing, it will be based on how much of delay you can have in that path, or how much of what you say segment area is available. All that decides how best connectivity you can give between any segment in your design. So this is that these are what we call it as wiring channels, or you can say routing channels also. These routing channels will be laid horizontally and vertically, and you should be deciding based on what is the length it is taking. And you have two aspects of wiring. That means segmented wiring is there. This wiring thing I'm saying. So I have logical blocks, 4 logical blocks are there, say 1, 2, 3, 4. Something like if I go for a shorter wiring, say each wire is of this short duration, say. Means that, see, if this is line 1, if I mention, I want to connect line logic element 1 to logic element 4, I need to have almost 3 delays here, because each node or each point of connection is to be programmed. It is not as simple as showing a dot here. Now this has to be programmed. That means 4 programs almost has to be given to reach this segment. Okay. Another thing is, if I have the segmented, say another segment, something like this, lengthy wire. So another block if I have, so it is connecting that directly to the second to second sort of thing. The delay is more, but here delay is less. Between two nodes, I am saying, between two nodes delay is less, and to connect first to the last one, say, it is requiring more number of program bits to be given. Whereas for the second one, the delay is little bit more, the number of program bits are less. And third, if I take directly the lengthiest path, delay is more, the programming bit is coming down. There is something like we have to forego something, either a length or the number of program bits sort of thing. This is segmented wiring, we say. This aspect we call it as segmented wiring. Now, if I want to, if I don't want to have a segmented thing where I can have only a fixed length of uh, wiring sort of things, fixed length, then I can use what is called as offset wiring. What is offset wiring is, my length is fixed. That means, see here, we are ending that at a similar point. An offset, you can have ending at any point. Say, I'm using this of this length, say. I repeat the same length to the next wire also, or next line also, but this line or this wire, I start at second and it will extend till third. That means it goes till fourth. So this is offset. That means that the ending is not constant. Like you don't have an ending point at the same stage. You can have at the varied stage. This is offset. But what is the difference between this and this is, the delays are different. Delays will be fixed. And your the programming points or programming bits is fixed in the offset sort of thing. So when we are taking these type of designs, the every wiring or every segment has to be programmed. That means, programmed means it has to be configured. Configuring or programming is same, the name is same. Programming has to be done to interconnect the segments. Okay, when as a designer, if he is designing or developing an FPGA, what his goal or his aim has to be is, in a given space, say this is my FPGA space, say, in a given space, how much of logic I can fit or how many blocks I can fit into that has to be first identified, and how many number of input output pins has to be given for a given area and given number of logic blocks inside. Say I'm saying all different logic blocks in a given space, how many such blocks I can incorporate, and how to address all these segments, how many number of inputs I have to give or how many number of outputs I have to take has to be decided. And doing so, what should be my speed of the complete design, at what rate it should run, or completely give the output has to be defined. So these questions, if the designer will be taking care of, okay, and doing so, what are the other things he has to put a point is, the interconnects, are they properly connected? Am I able to address or connect to all the segments in the blocks what we have? Okay, and how many number of interconnects I need to have? What is the structure of the interconnection? Structure is also important. I'll tell what is that structure. Okay, and how many pins I have to have, maximum or minimum sort of thing, that number you have to identify. And doing so, this also has to be packed with low cost. Cost should be low, size should be low, but efficiency should be up. That sort of thing, if it is addressed properly, like we can say that it is a highly efficient FPGA what it is getting. Now can I take this? Okay. A sample of, say, SRAM based FPGA, if I can define. Now, this SRAM based FPGA will be holding, this will be holding the instructions, or what you say, the configuration in the static memory. That is the difference you have, whereas in antifuse that is different. Okay, that is transistor level sort of thing, like switches we try to use. So FRAM based will be holding their configuration, that means the program will be stored in the static memory, and the output of this memory cell will be directly connected to another circuit, so that like a direct interlinking of one block to the other can be happening. Okay, and the control of, that means this memory cell will be directly connected to another circuit. Okay, and the controlling of this will be done by the circuits that are configured inside. Okay, as simple as saying that the state of uh, memory, okay, cell will be continuously controlled in the circuit that is being configured. Okay, so here what is the advantage of using SRAM is that it can be easily reprogrammed. Okay, that means you can use them without removing that from the circuit or the design itself. You can reprogram them, and you can reprogram them for multiple number of times. So you can say that a reconfiguration is possible. That is one basic advantage you have using SRAM sort of thing. And these are dynamically reprogrammable, we can say. What is this dynamically is, like during the operation itself, that means another logic is running, even then you can reprogram or do a new program on to your SRAM. Okay, then one more thing is, these are the standard logics or standard cells in your designs. Like if I take a DRAM in place of SRAM, why we are not choosing DRAM is, what is the reason is, actually this is 4 times of SRAM. Actually this will be having 4 times of SRAM thing capacity, but though this DRAM is very denser, it has to be refreshed frequently. This is refreshing iteration that is needed, which makes that to be disadvantage. So DRAM won't be used for our FPGAs. And what is the major disadvantage of this SRAM is that it will be burning more amount of power. Even if it is not in use also, it will be taking much power. Okay, and more of the what you say, noise susceptibility is there for SRAM. But other than that, your SRAM is very much useful, or what you say, advantageous comparatively. And what is the basic logic element of your SRAM is, like in this aspect, it will be a simple lookup table sort of thing, and using a mux, as simple as this. What is the lookup table element? Normally when we take a mux, n is to 1 mux sort of thing, what we take, this is how many number of selection lines you have, that much 2 power m should be equal to n, na? 4 is to 1 sort of thing, if you are taking, means that the size of the lookup table will be this. Okay, let me put that into a schematic sort of thing. Say, if this is your lookup table, which is able to give 2 power m combination of inputs to a mux. Okay, mux is of say 2 power m. So 2 power m is this one. So this will be your output. What is the logic we are putting in here? Based on how many number of selection lines you are having, that many number of what you say mbit information you are able to give to your mux. Now what is the capacity here is, say these are mbits, say you are having 10 bits in your the complete memory size, say 10 bits can be reshuffled. 10 bits of information can be reshuffled. That means a complete combination, if you take, what is the capacity of your SRAM is, it can represent 2 power 2 power m, I am saying 2 power 2 power m combinations it can represent. That means reshuffling of the information you can do at the locations, each location. That is the flexibility you are having. Okay, and this simple logic will be having an and or logic gates used and a mux implemented, and you can have a flip-flop also. In this, a flip-flop can be taken into a memory aspect, where if I use a flip-flop through a mux, say if I'm using a flip-flop through a mux, what it can do is I can store the data or I can directly take the data. That is the flexibility you have. Okay, something like I can store the data and I can give the data at the later portion also. So logic elements, generally it will be having the registers or latches or flip-flop sort of thing along with the combinational logic. Okay, and this will be able to implement a direct information or a stored information. So this is a complete, what you say, a simple description of an SRAM. So can I take an example of say Altera, fellow, Altera logic. What does this Altera SRAM has? Is a combination of a lookup table and a carry chain, and a cascade chain is available. This is the major blocks we are having. Okay, and this will be having the data inputs. This is data input. Okay, and this is carry in, and this is cascading. I think you must have read about cascade and cascode in your basic electronics. Cascading and cascoding. Synchronous clear or load logic is available, and where you can load or clear the data, and this will be taken through a mux having a D flip-flop as a storage segment, and this can be choosing a data directly from the cascaded thing or the stored thing. Okay, now this data, third bit will be here. I can take here. I'll tell what is the use of that actually. And here you will be having an asynchronous clear or preset or load logic segment, where based on either a chip reset signal or load signal or clear signal, this D flip-flop will be operating accordingly. This D flip-flop will be accordingly operated. That means this D flip-flop, we can use it as a JK flip-flop, T flip-flop, D flip-flop, like normal flip-flop, all segments or all modes we can use here. Now for this we have two clocks given. What are those clocks also I'll tell you. Clock 1 and clock 2 will be there, and this is enable 1 and enable 2. So this is chip enable sort of thing. Chip enable for D flip-flop. Now here one more mux will be there, where this will be your, this is Q now, Q will be one input and this fellow will be another input. Okay. So this is your single logic element of Altera Apex 2. Now this segment, this complete segment we can use for a normal operation or arithmetic operation or counting operation also. Okay. So when we take this segment, complete segment for say a normal operation, how this looks like is, it will be a, this lookup table will be a 4 input lookup table sort of thing. This is an arithmetic operation. If we are using this logic element for arithmetic operation, say this will be acting or selecting one of your data. That means D3 I have given, this D3, this D I am putting here. I think this is little bit, I'll move it. Okay. This flip-flop comes here now. This not flip-flop, mux is coming here. Now I'm taking D3, this D3, D1, D2, D3, if to be specific, D1, D2, D3 and D4. Okay, and this will be D4 connected, and the other input is carry in coming from here, this one, and D1 and D2 will be your inputs. For arithmetic operation, how this is taken up, I'm drawing now. And an AND logic will be there, which will be taking the cascade input. Okay, and this will be going to your mux, the third pin of your D3. This is an arithmetic operator, okay, which will be taking the D flip-flop, and this segment is your cascade output actually. Cascade in, cascade out. Okay, that will be taken to your one of the mux and the other D flip-flop, and these two will be taken to one. So this is your arithmetic operation. When you are performing arithmetic operation, this logic block will be used like this. So the same blocks we can use for counting operation, or something like you can reconfigure that, not reconfiguring, programming that for using that for something like a counter mode. So if I'm using this as a counter, the same blocks, but what we are taking here is 3 input lookup table sort of thing we take. For counter, 3 input lookup table LUT we will be taking, 3 input LUT. Okay, and this will be taking this D1, D2, and this will be taking, what you say, you can say that this is carry in has to be there, this is carry in, this carry in will be taken from a mux, or sorry, through a mux. If this is carry in, this will be taking the segment of this segment is there na? From this it will be taking that. I'm not redrawing that. Okay, what is the first segment difference only I am giving you, and this will be D1 and D2 taken up. This will be carry out. So this is your this same segment will be repeated. This will be acting as an counter operation. Okay, so something like the same logic element, you are able to configure that for different operations, or what you say, different functions. You are redefining the uh, internal connectivities. Okay, what are these interconnection networks what we are having? Okay, an SRAM based FPGA uses the SRAM to hold the information of the program of the interconnect. So it can be reconfigured within the logic element. But this interconnect point, like if you normally we call it as connection box, the interconnect point, all the points are what I have shown here in the previous thing. See here, this one, this we have taken. These are interconnect points sort of thing. These interconnect points, whatever we are having, should be configured. We are saying that configuration that we are performing is that is connection box. Through connection box we say, what is that connection box is? It is something like a simple using a pass transistor. The connection box will be developed. It is pass transistor gate, as simple as this. Like see here, a D flip-flop we try to use, whose output is given to a pass transistor. Hope you have read all this in your basic electronics. Transistor. Now what is this function is, see, when this is your gate of the pass transistor. See, the program connection between the two wires is made by this CMOS transistor, pass transistor. Okay, it is controlled by the static memory. This is static memory. No, SRAM is your D flip-flop format. No? So a bit value, what is being provided here through this D register, when the pass transistor gate is high, that means if this fellow is 1, the transistor will be connecting the two wires. Okay, when the gate this value is low, it will be open, it will be not connecting the two wires. So using this logic, that interconnections will be defined between the logic elements. It is as very simple logic of the connections what will be used. So for getting this connectivity of every logic element in your FPGA, we have something called as GRM, that is General Routing Matrix. Okay, this will be using this general routing matrix is of having these segments. This will be repeated. Okay, and this general routing matrix will be using the horizontal and vertical wiring, or horizontal and vertical channels, and between the combinational logic blocks, each logic blocks you will be having the wiring in between, and how many number of lines that you can run is decided by how many number of or what is the space you are having on that base. Okay, so generally this is something like using hexaline sort of thing, or 12-bit line can be there, or 24-bit line can be there. based on what is the size or what is the space available, the routing matrix will be having that many number of bits available for, or what you say, the per length, how many number of bits are there for connecting. Okay, so a single line is a 24 single line will be connecting that to the nearest we can say that left, right, up or down sort of thing. So for that, 12 bits for horizontal, 12 bits for vertical sort of thing will be divided. And again, you'll be having something like column and row matrix format, what we have seen, the same sort of routing will be given. Okay, so this FPGA configuration, when we are speaking, how we will be configuring them? This is about something like connections, we said. The configuration means um, the scan chains will be used. Again, we are seeing this term scan chain. What is this scan chain? We have used that for generating signatures and all, for testing different ICs on one slot sort of thing. We have used the scan chain between the blocks now, if you remember them. So this sort of scan chains will be used for configuring the um, logic elements. Okay, and who will be controlling this scan chain is your tap controllers, using tap controllers. The boundary scan, the tap controllers, all those segments will be coming into picture now. Okay, so what are permanent FPGAs or permanent programmed FPGAs is, this will be configured when you are giving a power. Okay, at power up they will be configured, and it will be something like the two technologies are used for the program that will be set up. One is anti-fuse, the other one is flash. Okay, so there are two technologies used to build this FPGAs to configure only once. Okay, what is this anti-fuse sort of technology is, between two metal conducting metal plates, say metal 1 and metal 2, say you are having metal 2 and which is connected to a substrate sort of thing, say this is your substrate. There will be an anti-fuse wire. This is anti-fuse wire sort of thing we say, and this anti-fuse wire, like it will be connecting the metal 1 and metal 2 wire by the amount of the voltage that is applied across this anti-fuse. Okay, so when the programming voltage is applied across this anti-fuse, it makes the connection between the metal line 1 and the metal line 2. That means above and below metals will be connected, and this is done through a wire sort of thing. So this is somewhere around 100 ohms of resistance it will be. And if it is overcoming that 100 volt, the voltage what you are applying is overcoming that, it will be able to give a contact sort of thing. So when you are not applying any voltage, what is by default available is, it is open fuse. Okay, it is normally open or disconnected stage it will be. When you want some connection to happen, and voltage will be applied and it will be making a contact sort of thing. Okay, this is like using an anti-fuse thing. If it is a flash FPGA, like that flash FPGA will be using the transistor thing, like it will be using flash transistor and the programmed transistor sort of. It's a simple transistor only. One function of one transistor will be for flashing and the other function of the transistor will be for programming. Okay, so a floating gate will be developed between these two transistors in such a way that something like say one transistor I take, say this is my connectivity substrate. Between substrate I'm having a base sort of thing, say. Okay, this is my gate. I'm taking this through the other gate. Okay, this I'll be using as a flash one, and this I will be using for a program transistor. And this is the word line, say. This is the word line. The gate here will be floating. This is floating gate, we say. This is floating gate. Okay, this is something like a high quality programmed uh, read-only memory sort of thing, the flash FPG. It uses the floating gate structure, and which will be holding a capacity in the capacitance format. There, it will be storing some leakage charges. Okay, that will be controlling the gate of the transistor. Okay, so this will be something like very sensitive sort of thing, where the connection points, it will be in between, that read write operations has to be performed based on the gate potential what is available. Okay, so this will be in place of antifuses, flash thing can be used, but there is a need of high efficiency or professionality needed for designing or using these type of switches. Okay, so when we are using these logic blocks, or when we are taking these logic blocks, how they are developed or how they are able to implement the logic is simple mux format only. Any level of mux you take, in if more number of inputs are there, the mux lines will be increased. Say if 2 lines are there, we take 2:1. If 4 lines are there, we take 4:1, or 2:1 you can take. That sort of logic only it will be taken for muxing, or what you say, selecting or transferring the inputs to multiple stages. Okay, so normal concept of taking this lookup format is mux itself. That is the conclusion you can make. So between your SRAM and your antifuse FPGAs, we need to have this input output pins, which are common. Both the ways input output pins are common. Okay, uh, when you are defining this input output pins, what are the things that has to be incorporated is that they should be like the pins of your input or output sort pins. They should be electrostatic discharge protected pins. Okay, they should be acting as a buffers. Output pins should be acting as a buffer with sufficient drive to produce sufficient signals to drive the next stage to which they are connecting. Okay, and you should be having three-state aspect also, not only input and output. You should have also three-state. That means if you are not using, it should be a tri-state, means it should be in high impedance. If you are not using, means that like isolation, perfect isolation of the device when it is not in use has to be maintained. Then in such a condition, then IO pins are perfect, or what you can say, they are able to uh, isolate the FPGA from any sort of reverse leakage values affecting them. Okay, and for all this, the interconnectivity and all, we have to go for the aspect of what is called as placement and routing. We are saying, what is placement is in space, okay, a provided space, how many logic segments or logic elements are there and where should I place them is the point of concern. That is placement. Deciding the positions of the logic elements on a given space to efficiently occupy the given space. That means there should not be much wastage, or it should not take more space than provided. That sort of aspect we have to see. So the placement will be determining the position of the logic elements as well as the IO pads or pins, we can say. So the logic elements placing and IO pins placing. When you take an IC, externally you'll be seeing this, but internally you'll be having the logic blocks now. So, and the next one is the interlinking of these IO pins with logic elements. All the logic elements has to be interlinked along with the IO pins. Okay, the connectivities between the pins and logic elements, it is routing. Routing is the connectivities between the logic elements and all your IO pins. Okay, what is the perfect placing? Something you have a term called as, one second, say rat nest plots, we say. That means, say, when we have to estimate the length. Say I have a few segments, okay, and another few segments are here, something like this, or individually independent blocks and logic elements I'm having. Okay. What is the length of the connectivities between every block? Okay, that will be deciding what is the routing length or what is the wiring. That calculation we have to see. So estimating the length of wire by measuring the, what you say, the distance between the pins and its connect. It is plotted, and that we call it as a rat nest plot. Okay, so this type of wiring, zigzag wiring, what I have given here, it is a bad wiring, we say. A good placement or good wiring is a straight, simple and clear cut of connectivities. That means the logic elements, when I am placing, if there is a link between 1 and 2, then I'll place them nearby. If this 1 and 2 are not linked, maybe I can place it here. Okay, that decides that placement will decide where each logic element has to be put onto my space or the given space. Okay, and where I place, how much of wiring it takes to connect them, it is decided, the efficiency of wiring is decided by how much shortest path we are able to connect them. That is routing. Okay, so this placement, we have to see that the area of the layout and the delay in the wiring has to be evaluated in parallel. So the wire distance, how we try to take is by calculating the Euclidean distance between the 2 points. Know that? Euclidean distance between 2 points. Okay, which also gives the half parameter thing, like a horizontal and vertical wiring if you are taking. Okay, calculate the Euclidean distance, that will be giving you what is the efficiency or what is the wiring distance you are able to contain. Okay, this measure is called as Manhattan distance also. Half distance is Manhattan distance, this one. Okay, two ways you are able to cluster them. Something like top down approach of clustering you can do, or bottom up approach of clustering you can do. Two ways you can cluster the segments, or bottom up, if you take, it is clustering. Top down, it is partitioning. Yes or no? Bottom up means we are trying to group them together, no? So it is clustering. Top down means we are dividing. So it is partitioning. So this way we have to like uh, normally do the placements. Something like say I have points somewhere like this. Okay. First, I try to see that this is linked like this. Then I measure that and I try to see that can I put that into one place sort of thing or something like this. Say if they are placed this format. Say. First, I do this type of connectivity. Say this is isolated. Now I can move this towards and I can put it a little bit near, then I will be able to cluster that segment. This is grouping. Okay. By moving that near to, I'm able to cut down the length. Now, this length I'm cutting down in the path. So this is clustering. Something like partitioning means, say you have segments at scattered thing. First, we try to partition as the maximal division sort of thing. Then we try to shuffle them in such a way that you will be able to get each point or each node moving towards one segment. Okay, this is partitioning sort of thing. That means you are dividing that into groups. So these are the two approaches what we are taking for the placement and routing sort of thing. Okay, so you for routing we have two phases. Global routing is there. This will be selecting the general path, okay, and through the chip it will not determine exact wire to which it has to connect, but it will be a general path through the chip and it determines the exact wire segments that has to be used. That means there won't be primary level, there won't be any fixed procedure. It will be going through the flow and it will decide which one will be giving you the nearest or the shortest wiring path. That is global routing. Detailed routing is another element where first it will be selecting the exact set of wires that has to be connected. Here randomly it will be taking which wire is like which connection is taking you the shortest thing will be chosen. So instead of going for these two, this will be chosen because this is shortest. But detailed routing is first nodes or wire itself will be fixed, then there will be a connection between those two wires. That is a detailed routing. So these are all about your basic level of FPGAs. So I'll stop here. This is your syllabus, what you have for FPGA. So you can refer to your Van Wolf, the textbook, what is given as a reference there. Okay.
Ma'am, so for minor, we have all the syllabus, ma'am, like some mid.
Basics will be there. Yes. So Monday evening we'll be having minor na 5 to 5:30 or 5:30 to 6. What is the time you are saying?
5 to 5:30, ma'am.
5 to 5:30. Okay, done. So
And
you can, yeah, you can refer to Van Wolf for all the details of the simple topics what we have seen now. Say altogether combinational logics, sequential logic, and your testing, all these three comes together into your the attributes, this FPGA attributes as well as your configuration of FPGAs. Okay. So just refer them back in your textbook. What is that they are mentioning there? Okay. Accordingly, you can correlate them. Okay.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank God.
Thank you, ma'am.
Ma'am,
Thank you, ma'am.
I think even ma'am left, yeah. अरे यार
अरे कार्तिको, माइक्रो प्रोग्रामिंग से है या पूरा है?
माइक्रो प्रोग्रामिंग भी